Hello, all of you. Uh, Today, let's start with the programming time delay programs of 8086. In the previous lecture, we have studied as logical and arithmetic programming. So, we have studied different types of arithmetic operations like subtraction, addition, as well as logical programs like AND or XOR, NOT, and how exactly you can perform using the different addressing mode like registers, memory, or immediate data, right? So today we are going to learn the time delay programs. So writing a time delay programs that I have given the few steps here. Mostly, I'm not mentioning too much writing, or you can say the too much description into the slides. But in this slide, I'm going to write too much description. That is some special purpose that you can understand each and every step properly. Okay. So most of the time, I'm keeping the force on only diagrammatical slides. So let's start. So first we'll see how exactly the delay programs can be write. So every instruction in the 8086 require a definite number of clock cycle for its execution, right? So there is a some clock cycles, and according to the clock cycles you can generate the delay, or you come to know how much time duration required to execute such a program. Okay. The amount of time for execution of an instruction is obtained by multiplying the number of clock cycle required for the execution of the instruction. Suppose any instruction required 200 cycles, okay, the clock cycles. Then by multiplying uh, with that execution of instruction and the number of clock cycles, you will get the how much time the program required to execute from starting to the end. So with the clock period at which the 8086 is running, the steps for writing the time delay program are as follow. Find the exact time delay, that is TD, required for the given application. Select the instruction, that is step 2. Select the instruction to be included in the time delay programs. While selecting the instruction and register to be used in the delay program, care must be taken that the execution of this instruction does not affect the main program of execution. Okay, while you are writing some delay instructions or some instruction that to count the time, what is the time delay, so that instruction should not affect your main program. Okay, so such a kind or such a way you can write the instructions. That is, any memory location or a register used by the main program must not be altered by time delay program, right? So if a register used in the main program is needed in the delay program, the content of that register is pushed into the stack before executing the time delay program. Okay, so whatever in the register that can be pushed into the stack. At the end of the execution of the time program, its original value will be popped from the stack and the control will be transferred to the main program. Okay, so whatever the value into the stack that can be popped, okay, and the control is given to the main program. Now step third, find the period of the clock at which the microprocessor is running by taking the reciprocal of the 8086 clock frequency. Okay, so you all know the frequency is the reciprocal of period, or period is the reciprocal of frequency. So when you will get the frequency of 8086, then you can easily find the period. So you can take the reciprocal of the 8086 clock frequency, that is T is the duration of one clock period of clock state. Okay, so that T is what? T is the duration of one clock period of a clock state. Now step 4, find the number of clock states required for the execution of each of the instruction in the time delay program. So each and every instruction is required some time or some period of the clock, and that should be calculated. So while for execution of the each and every step or instruction, there should be some time delay. Okay, so that need to be calculated. Then find the number of clock states, we can write it as m, needed to execute the loop in the delay program once. Okay, so sometime your program is having the loops means what? So same instructions can be executed multiple of times. So obviously it should require more time because the same code is executed repeatedly. Okay, so that's clock period or that delay of the program should be calculated, and by adding the clock steps required for each instruction in the delay program. Now step 5, find the number of times, that is count. Okay, to count n, the loop in the delay program has to be executed by dividing the required time delay td by the time taken to execute the loop. Okay, so what you have to calculate it, we have to calculate the count. So count means what, how many times that loop is executed. Suppose that loop is executed 10 times. Okay, that loop is executed 10 times, then divide the required time delay, okay, that is td, by the time taken to execute the loop once, which was m into t. So it means what, so how much time that loop is required to execute it, okay, that is divided by the td, that is time delay. So how much is the time delay, so you will get the how many counts. Okay, so you will get the total number of counts. Then the time delay is obtained using this method is sufficiently accurate to be used in a mini program. When more accurate delay are required, the programmable timer IC 8253 or the 8254 can be used. Okay, so this is how the 5 steps that is required. So we will take one real-time example, one program, and we will see the time delay of that program or how much time it will take to count. So here first we will take one example. Write a time delay program to generate a delay of 120 millisecond in 8086 based system that runs on a 10 megahertz of frequency clock. Okay, so what you have to calculate, we have to, okay, you have to write the programs. Okay, write a delay program to generate the delay of 120 millisecond. Okay, so we have to write such a program which can generate the 120 millisecond of the delay. So first, here I am giving you the time delay program. So instruction, so first we will take one instruction, move bx, okay, move bx comma count. So whatever is the count which is moved into the bx. Okay, so first we are going to do, so we have to find the value of the bx. Okay, so what is the first, we have taken one loop, that is L1. Okay, so decrement the bx. Okay, so bx is decrement and the two states for executions are required. After that nop, okay, so that instruction is executed and it take the 3 clocks or 3 time states. Okay, then jump if not 0 L1. So what it can does, so still the your bx will not become a 0 till you can execute the L1. Okay, means it's keeping executing decrement bx. Suppose decrement is 10, sorry, bx is 10, then decrement is 1, so it become 9, and then it will check does bx is 0, no, then again execute, then after 9 it will become 8, again it will check that does your L1 is 0, no, it is 8, then again it will decrement, so it becomes 7, 6, 5, 3, 2, 1, and when it will become 0, then it return to the main program. Okay, okay, that is return. Okay, so means what, it will return to the main program. So this is how this time delay program is executed. Now we will see how much millisecond and how the clock frequency it should be calculated. So in this program, the instruction decrement bx, nope, and jump not 0 L1, okay, from the loop as they are executed repeatedly until bx becomes 0. Once bx becomes 0, the 8086 return to the main program. So here continue with the previous. So number of clock cycles for execution of the loop. Okay, so how much clock cycles is required? So first extension required 2, then 3 and 16. Okay, jump not 0 is take the 16th clock cycle. So total 21 clock cycles. So we will calculate the how much time required for the loop execution. So we will calculate the total time. Okay, so what, how to calculate the total time then? So m is what, so we have calculated m is 21. Okay, and it is into t. Okay, and it is divided by the microseconds. Okay, so how much, 10 divided by 10 into 10 raised to 6, so that is nothing but what, 10 raised to minus 6, or you can say 1 raised to minus 6. So it will become 2.1 microseconds required for the, or it can be a time required for to execute the loop. Now we will count, then we will take the count. So what is the value of the count? That is nothing but your bx. What will be your bx? Then that 120 milliseconds is required to execution of the your program. So we will take 120 into 10 raised to minus 3. That way, that is nothing but your td. So td is same, that is total time. This is your t 2 raised to 2.1 microsecond, that is nothing but a 120 millisecond. It is the same. Okay, so we have just taken a different unit. Okay, so 120 into 10 raised to minus 3 divided by what? 2.1 into 10 raised to minus 6. Okay, so that is nothing but m into t and the total time, that is td. So your value become 57143, and in a hexa it will be a df37h. So you have, when you have load bx is equal to df37h, then your program will take on a your program will require 120 millisecond. That is nothing but what? So that is td here is given. Okay, 120, that is given, and this is nothing but your td, and this is your total time. So how much? 120 millisecond. If your program is taken to execute the 120 millisecond, then your bx value must be df37h. Okay, so the time taken to execute the delay program is approximately 120 millisecond. The knob included in the delay program is to be increase the execution time of the loop. To get more delay, the number of knob instructions in the delay loop can be increased. The exact delay obtained using this time delay subroutine can be calculated as shown in the next slide. Okay, so if you want to increase the more time delay, then you can include the NOP instruction. Okay, now write a time delay program to generate the, okay, same that we will continue here. So we have to calculate the exact delay. So the move bx count and return instruction in the delay program are executed only once. Okay, so which move program and return, that can be executed only once. The instruction, the jump not zero instructions taken 16 t states when the condition is satisfied. Okay, so that is z is equal to 0, and 4 t states when the condition is not satisfied, which occurs only once. So exact delay is what? So we will take in the 4 states. Okay, that is 4 into 0.1 in plus 2 plus 3 into 57 into 01. Okay, that will come to know now what is the count. So after calculation of this, you will get how much? 120 millisecond. Okay, so this is what the exact delay. Okay, so just point not 3 millisecond is increased. So exactly it is the same. So their errors in the previous calculation is very less. So the exact delay is also very close to the 120 millisecond. Okay, so previous we have calculated by given delay, and now after execution of the main and return, we have taken all the consideration of all the instruction, and after calculation of that exact delay, it will be like this. Okay, so the maximum count value that can be loaded in it is triple FH. This may put the limitations on the maximum time delay that can be generated using the above delay subroutine. So here is another example we will take. Write a delay program to create the time delay of 240 millisecond. Assume that 5 megahertz clock is used with a 8086 following is given. So again the same instruction is there. So immediate value you have given, that is the bx, and the decrementing that bx, that is your register, and we are using the NOF instruction, and the z not 0, so jump not 0 label. If the output is not 0, still keep jump on the label and return. So first we'll calculate the TD. So your TD is what? 240 milliseconds. So it will become 240 into 10 raised to minus 3 second. Then we'll calculate the total t state time period. So it will be nothing but what? 1 into, sorry, that is nothing but your 5 megahertz. So that is the frequency. So it will become what? 5 into 10 raised to minus 6 seconds. So that is nothing but 0.2 microsecond. Okay, and what is your number of t states in the one loop? That is nothing but 16 plus 3 plus 2. So total is how much? 21. So we are multiplying that 21 with a 0.2 microsecond over here. Okay, 0.2 microsecond means 0.2 into 10 raised to minus 6 into 21. And how much is the TD? So TD is calculated here, that is 240 into 10 raised to minus 3, that is we are dividing. So your formula is what? TD upon your m. Okay, TD upon your, sorry, m into t. Okay, so that is your total period into number of loops. Okay, so your final value will be df37h. Okay, the same value. If you increase this t, if you increase this clock frequency, okay, your this value will become less. Okay, so this is how you can calculate. So here is another. So now if you calculate the exact delay, so that is nothing but what, how to calculate same program. So exact delay is what, generated delay plus what, 4 plus 8 into 12, sorry, 4 plus 8 minus 12 into 0.2 microsecond, that is nothing but approximately. So the both are same mostly. Okay, so how this 4 plus 8, so we have not added this 4 and 8 in a previous, so we are adding those instructions into the your new while calculation the new time delay. Okay, so you can do the one more practice for your home. So here is one example. Write a delay program to create a time delay of 5 minutes. Okay, the 5 minutes. So first you calculate the seconds. Assume that 10 megahertz clock is used with the 8086. So you can solve it and kindly write your answers in a comment. Suppose here is a micro and m. Suppose that number of instructions occur repeatedly in the main program. The program listing become lengthy. In such a situations, a macro definition, that is a label, is assigned with the repeatedly appearing strings or instructions. The process of assigning a label or a macro name to be repeatedly appearing string of instruction is called macro definition. The macro name is in then used throughout the main program to refer that string of instruction. Sometimes what happen, the some code or some instructions can be repeatedly used, or some part of the program can be repeatedly used. For that purpose we are using the label, and there is another method, that is a macro. Okay, so you can define the macro, and that macro you can use everywhere. Okay, so here is one diagram that if you go into the C or C++, there is also the functions kind of things. Okay, the function is different, there is a macro is also available in the C. Okay, so you can similarly that macro can be used here. So I am writing here definition of the macro. So calculate macro, so move x comma bx, add x comma bx plus 2, move si comma x, and end m. Suppose what I have done, I have written this program. So calculate is the macro name. Okay, this calculate is the macro name. So while I am using the this program, I am always mentioning only calculate. So and the macro is used and two successive data in the memory whose offset address is present in the bx, and the result is stored in the memory at the offset address in a si. Using parameter in macro definition, the programmer specifies the parameter of the macro that are likely to be changed each time to macro is called. The macro given before the calculate can be modified to calculate the result for the different sets of the data and store it in the different memory locations as follow. So you can write calculate macro operand result. So this is the program, and you can rightly using the specify the parameter of the macro that are likely to be changed each time the macro is called. Now we will write one program here. So program to be find that the average of 10 bytes type data stored in the array of a data segment. So I will take one data segment over here. So data one segment, and data segment starts here. So I will take one array. That array is having the different numbers. Okay, db 12 23h. Okay, so array db, I am taking one name to the array, and these 10 numbers I am taking in that. So 12 23 44 7 56 0 abh 73 44 0 ab 0 aeh and 0 ah. Okay, so there are 10 bytes we have stored. Now we will count, so we'll use the count which number of bytes in the array. Okay, so how many numbers in the byte, so that we have taken the in a count, that is count equation. So we taken one count equal 10. Okay, so we have taken one variable, it count the how many numbers stored into the array. Okay, now we will take the average. average of this db. So db means what? So total number of db is given the name to the array, so it will mention the each and every numbers into the array. So average db 01 dup 0. So reserve 1 byte to store the result. Okay, we have store the 1 byte, okay, or we save the 1 byte to save the result. Okay, so after the doing the average, your result will be stored and data 1 ends. So data segments end. Okay, so that is what the program to byte to find the average of 10 bytes of the data bytes or data byte type data. So here it will continue now. So code 1 segment, so we will start. So move x data 1, so segment address of data 1 is move to ax, the move ds comma x, so move ax content to dx. So whatever is in the ax, okay, here we will move into the ds. Now move si comma offset array, so offset array address of array to si. So whatever is the offset array, so means what? Offset means first address of the array, that is move into the si. So whatever, suppose db0, db1, db2, suppose that db0 is having some address that can be moved into the si. Now XOR ax into XOR ax and ax. Okay, so clear ax and clear fact. So if you do the XOR, so all the x will become 0, or it can be a clear. And the move bx to 00h, so clear the bx is also clear. And the move cx, okay, move cx into the, so move the count of into the cx. Okay, so here is the, you will get the total count. Then in the next again move si to bl, so move 1 byte from array into the bl. So whatever is the byte, so we'll move this byte into the bl. Okay, now add ax and bx, so whatever is in the ax and bx we will add that. Increment si to point to the next byte. Now what happened, suppose si is 0. Now what? Now we have added ax into bx, so result is stored into the ax. Now we will increment the si, so si will become 1. So whatever the value of si, okay, that si is nothing but the array. Okay, so this is your array. So this is 0, 1, 2, these are different values, 10, 20, whatever we have mentioned. So first 0, okay, that is moved into x. Now 1, whatever the value at si 1, that will be moved in, that will be add with the ax. Okay, so it will give the loop. Next again move dh to count, so whatever the count to dh, that will move into the dh. So divide ax by ch. Okay, so here divide dh means what? Divide whatever will value in the ax with the ch and move the average into l. So whatever the average will become, that will be move into the average. So that is nothing but your al, and the code 1 ends. So likewise the average is calculated, so each time by taking the next. So whenever loop next, it goes here. So again you are keep adding, again goes there, keep adding, goes there, keep adding, up to where? So 10 na, so 0, 1, 2, 3 up to 9. So when it will si will become 9, it will come out of the loop, and when count will be 9, it will come up. Okay, now divide dh. So how much count? Suppose there are 10 count, how many times this loop is moved? 10 times. So we have to calculate the average. So your ax will contain the addition of all the 10 numbers, and we dividing with the 10. Okay, so you will get the average. How will calculate the average? Total addition of the total number plus divide by total numbers. So here you can calculate, and your final value move into the average, and you can end the code. So this is how the program is can be done to average the 10 bytes of the data. So this is done for the today's lecture. I hope you understand the things, how to calculate the time delay, as well as how to calculate the average of the numbers using the assembly language. So thank you very much for today's lecture.